And now in this lecture we'll answer on two questions. In the first question we find out the area of this green shape. In the second question we find out the length of this line segment AP that is equals to x using two different methods. So we'll start with the first question. In the drawing we have a semicircle. BC equals to 10 units in its length. That is to say the diameter of this semicircle is equal to 10 units. In addition, we know that PC equals to 8 units in its length. This is angle ABC, that is a right angle. Again, our task is to find out the area of this green shape. So first of all, we'll join points P and B together by a straight line. By joining points B and P, we create that peripheral angle BPC. Peripheral angle BPC subtends on BC, that is the diameter of this semicircle, and according to rule 5, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its side. So if it's equal to rule 5, according to rule 5, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So in the drawing we have a circle. AB is the diameter of this circle. Peripheral angle AB subtends on AB, that is the diameter of this circle, and therefore the size of peripheral angle AB is 90 degrees according to this rule, rule 5. So we can actually implement rule 5 in our drawing. Why? Because in our drawing we have peripheral angle BPC that subtends on BC, that is the diameter of this semicircle, and therefore according to rule 5, the size of peripheral angle BPC is 90 degrees. It is equal to 90 degrees in its size according to rule 5. In the next step, we will implement the Pythagoras theorem on the right triangle BPC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, in the right triangle BPC, BC is the hypotenuse, and therefore the square of the hypotenuse is BC square, and BC square must be equal to PB square plus PC square. Here by PT is a operation for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle BPC, BC square, that is the square of the hypotenuse, equals to PB square plus PC square. BC is 10, therefore BC square is 10 squared, that is 100, and it is equals to PB square. PB is the missing side, so we leave it as it is. It is PB square plus PC square. PC is 8, therefore PC square is 8 squared, that is 64. So in total we found out that 100 equals to PB square plus 64. Here we will subtract 64 from this equation, and we get that 100 minus 64 is 36 equals to PB square. So here we take a root out of this equation, and we get that PB, the missing side PB, is equals to the square root of 36, that is 6. PB, the missing side PB, equals to 6 units in its length. It is given as the question that AC is a straight line. So if we focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to the rule that said that the sum of the angles on one side of a straight line is equal to 180 degrees. So each angle we have on the left side of AC at point P, we have this angle that is right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its side. So in the right triangle APB, we define angle BAP. This angle is alpha. So in the right triangle APB, this angle equals to alpha. This angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. It is given as the equation that the big angle ABC is a right angle. So this is the right angle. We already found out that angle ABP, this angle equals to 90 degrees, and therefore the size of this missing angle PBC must be equal to the size of the big angle that is 90 degrees minus the size of this angle that is 90 degrees minus theta. 90 degrees minus alpha. 90 degrees minus 90 degrees minus alpha equals to 90 degrees minus 90 degrees is 0, and we have minus times minus is plus. So 90 degrees minus 90 degrees minus alpha equals to alpha. So this missing angle must be equal to alpha. Another way to see why this missing angle equals to alpha, because alpha plus 90 degrees minus alpha is 90 degrees. That is the side of the big angle ABC. So in the right triangle BPC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So in the next step, we'll prove that the right triangle APB is similar to the right triangle BPC according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, both those two angles are equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, both those two angles are equal to 90 degrees, and therefore they are equal to each other. So we can prove that all the figures of the right triangle APB are correspondingly equal to all the figures of the right triangle BPC, and therefore those two right triangles are similar to each other according to angle similarity rule. So it is known if we found out that the right triangle APB is similar, this is the sign of similar to the right triangle PBC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle APB over side BC of the right triangle BPC is equal to side AP of the right triangle APB over side PB of the right triangle PBC, and it is also equals to side PB of the right triangle APB Actually, PB is the common side that belongs to both triangles. So it is equal to side PB of the right triangle APB over side PC of the right triangle PBC. If you regard from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle ABP over side BC of the right triangle PBC is equal to side AP of the right triangle APB over side PB of the right triangle PBC, and it is also equal to side PB of the right triangle APB over side PC of the right triangle PBC. AB is the missing side, so we write as it is. Over BC equals to 10 units in its length, and it is equal to AP is the missing side, so we leave it as it is, over PB equals to 6 units in its length, and we have PB again, that is 6, over PC equals to 8 units in its length, according to what is given in the question. So in total, we actually found out that AB over 10 equals to AP over 6 equals to 6/8. So those two expressions are equal to each other. Therefore, we get the first equation from those two expressions. According to the first equation, we get that AB over 10 is equal to 6/8. Again, AB over 10 equals to 6/8. So here we multiply this equation 1 by 10, and we get that AB equals to 6 times 10 is 60 eighths, 60 over 8. Here we divide both the numerator and the denominator of this number by 4, and we get that 60 over 4 is 15, and 8 over 4 is 2. So in total, we should find out that AB, the missing side AB, equals to 15 halves units in its length. Okay, this is the missing side AB, that is equals to 15 halves units in its length. Those two expressions are also equal to each other, so we get the second equation from those two expressions. According to the second equation, we get that AP over 6 equals to 6/8. AP over 6 equals to 6/8. Here we multiply this equation by 6, and we get that AP equals to 6 times 6 is 36/8. So here we divide both the numerator and the denominator of this number by 4, and we get that 36 over 4 is 9, and 8 over 4 is 2. So in total, we should find out that AP equals to 9 halves in its length. This is the missing side AP, that is equals to 9 halves units in its length. In the next step, we define the center of this semicircle. This point is point O. The diameter of this semicircle BC equals to 10, therefore the radius must be equal to 5. The radius BO must be equal to 5. The radius OC is also 5. We join points O and P together by straight line. O is the center of the semicircle, P is the point of the semicircle itself. Therefore, OP is the radius of the semicircle, that is equal to 5 units in its length. In the next step, we define angle POB. This angle is theta, and I will present you we'll present to you the law of cosines, and we will implement the law of cosines in this triangle POB. Actually, the law of cosines is true in any triangle. This is triangle ABC that could be in any triangle. In this triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, side BC equals to C units in its length. This is angle BAC. The side of angle BAC is theta degrees. According to the law of cosine, the following equation is true: that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So we can actually implement the law of cosines in this triangle POB. According to the law of cosines, in triangle POB, the following equation will be true: cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. Repeat again, in triangle POB, according to the law of cosines, the following equation is true: that cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. So cosine theta equals to 5 squared is 25, plus 5 squared is 25, so 25 plus 25 is 50, minus 6 squared. 6 squared is 36, so it is 50 minus 36, that is 14. In the denominator we have 2 times 5 times 5, that is 50. So in total, if we found out that cosine theta equals to 14 over 50. Cosine theta equals to 14 over 50. We would like to find out the value of theta itself. In order to find out the value of theta itself, we'll use the rule that says that the inverse function cancels out the action of a function. Again, the inverse function cancels out the action of a function. So I'll give you an example. We know that we have the square, and the inverse function of a square is a root. Again, the root is the inverse function of the square. So if we take number 3 and we square it, that is to say 3 square equals to 9. 3 square equals to 9. So the result of the operation of the square on the function of the square on number 3 is 9. Now if we operate the inverse function of a square that is a root, that is the square root, on the result that is 9, the square root of 9 is 3. In this way, we got back number 3 again. So in order to get back the original number or the original angle, we have to operate on the result, the inverse function. In this way, we get back the original number or the original angle before operating the function on the original number or on the original angle. So here we operated the function cosine on angle theta, and the result is 14 over 50. In order to get back angle theta again, we have to operate the inverse function of cosine, that is arc cosine, on the result, that is 14 over 50. In this way we get angle theta back. And arc cosine of 14 over 50 equals to theta, and theta equals to 73.74 degrees in its size. Actually, you can find out the value of cosine 14 of arc cosine 14 over 50 by using any simple scientific calculator. So arc cosine of 14 over 50 equals to angle theta, and angle theta equals to 73.74 degrees in its size. So if you found out that this is angle theta, and the size of this angle theta is 73.74 degrees. Our task is to find out the area of this green shape. In order to find out the area of the green shape, first of all we have to find out the area of this segment, segment BP. So what is the area of segment BP? This is segment BP. What is the area of segment BP? From the drawing, it is very easy to see that the area of segment BP equals to the area of sector BOP. This is sector BOP. Minus the area of triangle BOP. So if it again, we should find out that the area of this segment BP, the area of segment BP equals to the area of sector BOP minus the area of triangle BOP. What is a sector? A sector is a portion of a circle with two radii and the arc between them. This is sector AOB. It consists of those two radii and the arc AB between the two radii. Actually, the two radii are defined as the legs of the sector. Angle theta is defined as the angle between the legs of the sector. And the area of this green sector AOB is equals to pi r squared, this is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again, the area of the sector equals to pi r squared, this is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. So we use the new formula in order to find out the area of this sector, sector BOP. This is angle theta, and we already found out that angle theta equals to 73.74 degrees in its size. OB equals to 5, BP also equals to 5, they are both the radii of the semicircle, is equals to 5 units in its length. So the area of this sector POP equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 73.74 degrees over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, and therefore pi r squared is 25 pi times 73.74 degrees over 360 degrees. The value of this expression is equal to 16.088 square meters. So if you found out that the area of this sector BOP is equal to 16.088 square meters in its size. Minus the area of this triangle BOP. BO equals to 5. PO and PB equals, actually this is triangle POB. OB equals to 5, PB also equals to 5, the above the semicircle is equals to 5, and PO, so actually triangle POB. This letter is B, and we have triangle POB, and PB equals to 6 units in its size. PBO. So PO equals to 5, BO equals to 5, and PB equals to 5. Actually, this is triangle POB that is defined as an associated triangle. Why? Because side PO equals to side OB equals to 5. So I copied the triangle POB again. So actually, this is the associated triangle POB. PO equals to 5, BO equals to 5, and PB equals to 6 units in its length. Triangle POB is an associated triangle because PO equals to OB equals to 5. PB is defined as the base of this associated triangle POB. In order to find out the area of this associated triangle POB, from the vertex O, we'll draw perpendicular on PB. Again, from the vertex O, we'll draw perpendicular on the base PB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and the base PB. This point is point M. By doing this construction, we can do the right triangle POB. According to the rule that said that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. The base PB equals to 6 units in its length. So half of 6 is 3. So PM is 3. MB is also 3. So in the right triangle PMB, 5 square equals to OM square plus 3 square. So 25 equals to OM square plus 3 square, that is 9. So here we subtract 9 from the equation, and we get that OM square equals to 25 minus 9, that is 16. OM square equals to 16. Here we take out all of this equation, and finally get that OM equals to the square root of 16, that is 4. So OM equals to 4 units in its length. Side OM equals to 4 units in its length. Now it is very easy to see, to find out the area of this associated triangle POB. The area must be equal to the base, that is PB, times the height to the base, that is OM, over 2. PB is 6, OM is 4, divided by 2. 4 over 2 is 2, and 2 times 6 is 12. So in total, we should find out that there are of this associated triangle PBO is equals to 12 square units in its size. So in total, the area of segment BP equals to the area of sector POB, that is 16.088 square units, minus the area of this associated triangle POB, that is equals to 12 square units. And 16.088 minus 12 is 4.088. So if we found out that the area of segment BP is equal to 4.088 square units in its size. Our task is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape is equal to the area of the right triangle APB minus the area of this segment, segment BP. So if it again, if we found out the area of this green shape equals to the area of the right triangle APB minus the area of segment BP. What is the area of this right triangle APB? Side AB equals to 9 over 2, that is 4.5 units in its length. PB equals to 6 units in its length. So the area of the right triangle APB equals to, we take the base of AP times the height to the base, that is PB, over 2. AP is 4.5 times PB is 6 divided by 2. 4.5 times 6 is 27 over 2. 27 over 2 is 13.5 square units. So in total, we should find out the area of this right triangle APB is equal to 13.5 square units in its size. Minus the area of this segment BP. We already found out that the area of segment BP is equal to 4.088 square units in its size. And therefore, the area of the green shape must be equal to the area of this right triangle APB, that is for 13.5, minus the area of this segment BP, that is equal to 4.088. And 13.5 minus 4.088 is equal to 9.412 square units. So in total, we should find out that the area of the green shape, that is the area that we are looking for this question, is equal to 9.412 square units in its size. But again, we should find out that the area of this green shape is equal to 9.412 square units in its size. So we finish with the first question. In the next step, I will present you the second question, and we solve the second question using two different methods. In the second question, our task is to find out the length of this line 970 feet is equal to x. We have to find out the value of x. So in the drawing, we have a semicircle. AB equals to 10 units in its length. That is to say, the diameter of this semicircle equals to 10 units in its length. In addition, we know that BC equals to 6 units in its length, and AP equals to PC equals to x. Again, our test is to find out the length of line segment AP is equal to x. So first of all, we define the center of this semicircle. This point is point O. The diameter of this semicircle AB is 10, therefore the radius must be equal to 5. The radius OA is 5. The radius OB is also 5. In the next step, we will join points O and P together by a straight line. Point O is the center of the circle, point P is the point on the circle itself. Point O is the center of the semicircle, point P is the point on the semicircle itself, therefore OP is the radius of this semicircle that is equal to 5 units in its length. Actually, by doing this construction, we can do the associated triangle AOP. Why triangle AOP is an associated triangle? Because AO equals to OP equals to 5. And we have the rule that says that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides in triangle, the associated triangle AOP, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the associated triangle AOP, alpha plus alpha is to alpha, and therefore this first basic angle must be equal to 180 degrees minus 2 alpha, according to the rule that says that the sum of the angles in a triangle is equal to 180 degrees. Likewise, in the big associated triangle APC, why triangle APC is an associated triangle? Because side AP equals to side PC equals to x. So in the big associated triangle APC, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. But we have already found out that the size of this angle is alpha. Therefore, the size of this angle must be also equal to alpha because they are equal to each other. So in the big associated triangle APC, alpha plus alpha is 2 alpha, and therefore this first basic angle must be equal to 180 degrees minus 2 alpha, according to the same rule that said that the sum of the angles in a triangle is equal to 180 degrees. Therefore, this first basic angle must be equal to 180 degrees minus 2 alpha. So in the next step, I will copy the big associated triangle APC and the small associated triangle AOP in a new page, and we will prove that those two associated triangles are similar to each other according to angle similarity rule. What is the size of side AC of the associated triangle APC? AC in total equals to 10 plus 6, that is 16. Actually, those are the two associated triangles that are coming from the original domain. This is the big associated triangle, triangle APC, and this is the small associated triangle, triangle APO. Here side AEP equals to x units in its length. Side PC also equals to x units in its length. In this triangle APO, AEP equals to x, AO equals to 5, and PO also equals to 5 units in its length. So, why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal also to alpha, therefore they are equal to each other. So if we prove that all the triangles of the right of the big associated triangle, triangle APC are correspondingly equal to all the triangles of the small associated triangle, triangle APO. And therefore those two associated triangles are similar to each other according to angle similarity rule. So I write it down, and we found out that the big associated triangle, triangle APC is similar, this is the sign of similar, to the small associated triangle, triangle APO according to angle similarity rule. And from the fact that those two associated triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side AC of the associated triangle, triangle APC over side AP of the small associated triangle, triangle APO is equal to side PC of the big associated triangle, triangle APC over side PO of the small associated triangle, triangle APO. So repeat again, from the fact that those two associated triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AC of the big associated triangle, triangle APC over side AP of the small associated triangle, triangle APO is equal to side PC of the big associated triangle, triangle APC over side PO of the small associated triangle, triangle APO. AC 16 over AP, AP is x, and it is equals to PC, PC is also x, over PO, PO equals to 5 units in its length. So in total we found out that 16 over x equals to x over 5. Here we will first multiply this equation, and we get that x times x is x squared equals to 16 times 5. So here we take a root out of this equation, and finally we get that x equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we have to only be 5. So in total we found out that AP is equals to x. This is line 7 that we are looking for in this question. It is equals to either 4 times square root of 5 units in itself, or in terms of numbers, 4 times square root of 5 is 8.94 units. But again, we found out that the length of this line 7 AP is equals to x. It is equals to either 4 times square root of 5 units in itself, or the length of this line 7 AP is equals to x is equal to 8.94 units in its length. So we finish the first method. In the next step, I present to you how to find out the length of this line 7 AP is equals to x using the second method. In the second method, we use the rule that we already used in the first question. The rule says that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. This is the big triangle APC. The big triangle APC is an associated triangle, while because side AP equals to side PC. AC is the base. The length of the base AC is 10 plus 6, that is 16. The length of the base AC of the associated triangle APC is equal to 16 units. So from the vertex P, we will draw perpendicular on the base AC. Again, from the vertex P, we will draw perpendicular on the base AC. So here this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and the base AC. This point is point M. According to the rule that I mentioned, the perpendicular PM to the base AC bisect the base AC. AC in total is 16, so each half must be equal to 8. The first half AM is 8, and the second half MC is also 8. So AM equals to 8 units in its length. According to the rule that I mentioned, AM equals to 8 units. It is the first half of the base AC. In the next step, we define the center of this semicircle. This point is point O. The diameter AM is 10, therefore the radius must be equal to 5. So the radius OA is 5. The radius MC is also, the radius OB is also 5. We join points O and P together by a straight line. Point O is the center of the circle, point O is the center of the semicircle, point P is the point of the semicircle is there, therefore OP is the radius of the semicircle, that is equal to 5 units in its length. What is the length of the missing line segment OM? OM equals to AM minus AO. Again, so I write it down. OM equals to AM minus AO. So OM in total equals to AM, that is 8, minus AO, that is 5. So in total OM equals to 8 minus 5, that is 3. So OM equals to 3 units in its length. OM equals to 3 units in its length. So in the next step, we'll implement the Pythagoras theorem on the right small triangle POM. So I copy the right small triangle POM in a new page, and we'll implement on it the Pythagoras theorem in order to find out the missing side PM. The hypotenuse PO equals to 5 units in its length, OM equals to 3 units in its length, and PM is the missing side. So finally, this is the right small triangle POM that I copied from the original drawing. According to the Pythagoras theorem, in this right small triangle POM, PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. So I write it down. PO squared, that is the square of the hypotenuse, is equal to PM square plus OM square. PO is 5, therefore PO square is 5 squared, that is 25. And it is equal to PM square. PM is the missing side, so we leave it as it is. So it is PM square plus OM square. OM is 3, therefore OM square is 3 squared, that is 9. So in total, we found out that 25 equals to PM square plus 9. Here we subtract 9 from this equation, and finally we get that PM square equals to 25 minus 9, that is 16. PM square equals to 16. Here we take a root out of this equation, and finally we get that PM equals to the square root of 16, that is 4. So the missing side PM is equal to 4 units in its length. This is the missing side PM, that equals to 4 units in its length. In the next step, I will copy the right triangle APM in a new page, and we will implement on it the Pythagoras theorem. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle APM that are coming from the original domain, according to the Pythagoras theorem in this triangle APM. PA squared, that is the square of the hypotenuse, equals to PM square plus MA square. So I write it down. PA squared, that is the square of the hypotenuse, equals to PM square plus AM square. The hypotenuse PA equals to X units in its length. That is the line segment that we are looking for. So PA square equals to X square, and it equals to PM square. PM is 4, therefore PM square is 4 squared, that is 16, plus AM square. AM is 8, therefore AM square is 8 squared, that is 64. So in total, we actually found out that X square equals to 16 plus 64, that is 80. So X square equals to 80. Here we will substitute 18 by 15 times, by 6 times 15. We will substitute 80 by 5 times 16. X square equals to 16 times 5. 16 times 5 is 80. So here we take out of this equation, and we get that X equals to the square root of 16 times 5. The square root of 16 is 4, and inside the root we left only with 5. So in total we found out that AP is equals to X. This is equals to either 4 times square root of 5, or in terms of numbers, it is equal to 8.94 units in its length. So we actually found out in both methods, we found out that the length of this line segment AP is equals to X is equal to either 4 times square root of 5 units in its length, or in terms of numbers, the length of AP is equals to X is equal to 8.94 units in its length. So we finish with the second question. In the next step, I'll start with the lecture. I'll start with the first question, of course. the first question, our task is to find out the area of this green shape. So in the drawing we have a semicircle. BC equals to 10 units in length, that is to say the diameter of this semicircle is equal to 10 units. In addition, we know that PC equals to 8 units. This is again ABC, this is a right angle. Again, our task is to find out the area of this green shape. So first of all, we join points P and B together by a straight line. By joining points P and B, we create a peripheral angle BPC. Peripheral angle BPC subtends on BC, that is the diameter of this semicircle. And according to rule 5, any peripheral angle that subtends on the diameter of the semicircle must be equal to 90 degrees in its size. Therefore, this angle is a right angle according to rule 5. In the next step, we implemented the Pythagoras theorem on the right triangle BPC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle BPC is BC, therefore the square of the hypotenuse is BC square, and BC square must be equal to BP square plus PC square. So again, the right triangle BPC, according to the Pythagoras theorem, here by PT is evaluation from Pythagoras theorem. According to the Pythagoras theorem, in the right triangle BPC, BC square, that is the square of the hypotenuse, equals to PB square plus PC square. The hypotenuse BC equals to 10 units in its length. BC is 10, therefore BC square is 10 square, that is 100. And it is equals to PB square. PB is the missing side, so it is plus PC square. PC is 8, therefore PC square is 8 square, that is 64. So in total, we actually found out that 100 equals to PB square plus 64. Here we subtracted 64 from this equation, and finally found out that 100 minus 64 is 36, so 36 equals to PB square. Here we took out of this equation, and finally found out that PB equals to the square root of 36, that is 6. This is side PB equals to 6 units in its length. In the next step, it is given us the question that AC is a straight line. So if you focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line AC at point P? We have this angle that is a right angle, plus this angle to the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle APB, we define this angle PAB as alpha. So this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. It is the sum of the angles in a triangle. It is given us the question that angle ABC is right angle. We just write now found out this angle equals to 90 degrees minus alpha. This is to say angle ABP equals to 90 degrees minus alpha. Therefore, this missing angle must be equal to 90 degrees minus 90 degrees minus alpha. 90 degrees minus 90 degrees minus alpha is alpha. So this angle, the missing angle here must be equal to alpha. Another reason that this missing angle must be equal to alpha, because alpha plus 90 degrees minus alpha is 90 degrees. That is the size of the big angle ABC. So this missing angle equals to alpha. This angle is right angle. Therefore, this first missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, we prove that the right triangle APB is similar to the right triangle BPC according to angles similar to. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, both those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So we should prove that all the figures of the right triangle APB are correspondingly equal to all the figures of the right triangle BPC, and therefore those two right triangles are similar to each other according to angle similar to. And from the fact that those two right triangles are similar to each other, so repeat again, if we found out that the right triangle APB is similar, this this is the sine of similar to the right triangle PBC according to angle similar to it. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle ABP over side BC of the right triangle PBC is equal to side AP of the right triangle APB over side PB of the right triangle PBC, and it is also equal to side PB of the right triangle APB over side PC of the right triangle PBC. And again, from the fact that those two right triangles are similar to each other, we derive that AB over BC equals to AP over PB equals to PB over PC. In the numerator of each expression, we have the sides of the right triangle APB, and in the numerator of each expressions, we have the sides of the right triangle PBC. So AB over BC equals to AP over PB equals to PB over PC. AB is the missing side, so we limit the cities. BC is 10, AP is the missing side, so we limit the cities. Over PB, PB is 6, and we have PB again, that is 6, over PC, PC is 8. So in total, we should find out that AB over 10 equals to AP over 6 equals to 6/8. Those two sides are equal to each other, therefore we get equation 1 from those two expressions. According to equation 1, AB over 10 equals to 6/8. Here we multiply this equation 1 by 10, and finally found out that AB equals to 10 times 6, that is 60 over 8. AB equals to 68. Here we divided both the numerator and the denominator of this number by 4, and finally found out that 60 over 4 is 15, and 8 over 4 is 2. So in total, we should find out that AB equals to 15 half units in its length. This is side AB, this equals to 15 half units in its length. Those two expressions are also equal to each other, therefore we created the second equation from those two expressions. According to the second equation, AP over 6 equals to 6/8. AP over 6 equals to 6/8. Here we multiply this equation by 6, and finally found out that AP equals to 6 times 6 is 36 over 8. Here we divided both the numerator and the denominator of this number by 4, and finally found out that 36 over 4 is 9, and 8 over 4 is 2. So in total, we found out that AP equals to 9 half units in its length. This is inside AP, this equals to 9 half units in its length. So, in the next step, we define angle POB. This angle is theta. Then I presented to you the law of cosines, and we implemented the law of cosines in this triangle POB. So, what is the law of cosines? Actually, the law of cosines is for any triangle. This is triangle ABC. That could be any triangle. This triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. This is angle BAC, that is equals to theta degrees in its size. This triangle ABC, that could be any triangle. The following equation is true, that cosine theta equals to h square plus b square minus c square over 2 times a times b. Again, cosine theta equals to h square plus b square minus c square over 2 times a times b. So if we implemented the law of cosines, in this triangle POB, according to the law of cosines, this triangle POB, cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. And again, the right triangle POB, according to the law of cosines, cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. So cosine theta equals to 5 square is 25, plus 5 square, that is 25, 25 plus 25 is 50, minus 6 square, 6 square is 36, so it is minus 36, and 50 minus 36 is 14. In the denominator we have 2 times 5, that is 2 times 5 times 5, that is 50. So in total we should find out that cosine theta equals to 14 over 50. cosine theta equals to 14 over 50. We would like to find out the value of theta itself. In order to find out the value of theta itself, use the rule that the inverse function cancels out the action of a function. Again, the inverse function cancels out the action of a function. I gave you an example. You have the function square, and the inverse function of a square is a square root. So if we take number 3 and we square it, 3 squared is 9. If we want now to get back number 3 again, we just have to operate on the result, the inverse function of a square that is a root, and the square root of 9 is 3. So actually, the inverse function of a square that is a root cancels out the action of a root, and in this way we get back number 3 again. Likewise, we operated on angle theta, the function cosine, and the result is that cosine theta equals to 14 over 50. Now, in order to get back angle theta itself before the operation of the function cosine on it, we have to operate the inverse function of cosine, that is r cosine, on the result that is 14 over 50. In this way we get back angle theta. And r cosine of 14 over 50 is angle theta, and r cosine of 14 over 50 equals to 73.74 degrees in size. So in conclusion, we found out that the size of angle theta is 73.74 degrees. Angle theta equals to 73.74 degrees in size. Our task is to find out the area of this green shape. In order to find out the area of this green shape, first of all, we have to find out the area of segment VP. What is the area of segment VP? From the drawing, it is very easy to see that the area of segment VP equals to the area of sector BOP minus the area of triangle BOP. Again, the area of segment VP equals to the area of sector BOP minus the area of triangle BOP. If it again, the area of segment VP equals to the area of sector BOP minus the area of triangle BOP. What is a sector? A sector is a section, a portion of a circle with two radii and the arc between them. The green shape AOB is a sector. Sector AOB consists of two radii and arc AB between the two radii. Angle theta is the angle between the legs of the sector, and the area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. We use the new formula in order to find out the area of this sector, sector POB. The area of sector POB must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 73.74 degrees, over 360 degrees. R is 5, therefore r squared is 5 squared is 25, so pi r squared is 25 pi, times 73.74 degrees over 360 degrees. The value of this expression is 16.088. So in total, we have found out the area of sector POB is equals to 16.088 square units in its size. And we have to subtract from the area of the sector the area of this associated triangle, triangle POB. Well, triangle POB is an associated triangle because side PO equals to side BO equals to 5. In the associated triangle POB, PB is the base of this associated triangle. And in order to find out the area of this associated triangle, triangle POB, from the vertex O, we draw perpendicular on the base PB. Again, from the vertex O, we draw perpendicular on the base PB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And we have the rule that the perpendicular to the base of an associated triangle bisects the base. Again, the perpendicular to the base of an associated triangle bisects the base. So the perpendicular OM bisects the base PB. PB is 6, therefore each half must be equal to 3. PM is free, and B is also free. By doing this construction, we get the right triangle OMP. According to the Pythagoras theorem, the right triangle OMP, PO squared equals to PM squared plus OM squared. PO is 5, therefore PO squared is 5 squared, that is 25, and it is equals to OM squared. OM is the missing side, so we use as it is, plus PM squared. PM is 3, therefore PM squared is 3 squared, that is 9. So in total, we have found out that 25 equals to OM squared plus 9. Here we subtracted 9 from this equation, and we found out that OM squared equals to 25 minus 9 is 16. OM squared equals to 16. Here we took out of this equation, and we found out that OM equals to the square root of 16, that is 4. So the missing side OM equals to 4 units in itself. The missing side OM equals to 4 units in itself. Now it is very easy to see, to find out there of this associated triangle POB. There are friend triangle equals to the base of the triangles times the height of the base over 2. The base PB is 6, the height OM is 4 divided by 2. Again, it is the base PB times the height OM over 2. PB is 6, OM is 4 divided by 2. 4 over 2 is 2, and 2 times 6 is 12. So in total, we should find out that there of this associated triangle POB is equal to 12 square units in its size. And there of segment BP must be equal to there of this sector POB, that is 16.088, minus there of this associated triangle POB, that is 12. 16 minus 0.88 minus 12 is 4.088 square units in its size. So in total, we should find out that there of this segment BP equals to 4.088 square units in its size. Our task is to find out the area of this green shape. From the drawing, it is very easy to see that the area of this green shape equals to the area of the right triangle APB minus the area of this segment BP. Again, the area of this green shape equals to the area of the right triangle APB minus the area of this segment BP. Again, we should find out that the area of the green shape equals to the area of the right triangle APB minus the area of this segment BP. What is the area of the right triangle APB? AP is 4.5, PB is 6. So the area of the right triangle PB must be equal to the base AP times the height of the base, that is PB over 2. AP is 4.5, PB is 6 divided by 2. 4.5 times 6 is 27 divided by 2. 27 over 2 is 13.5. So in total, if you found out that the area of this right triangle APB is 13.5 square units in its size, we have already found out that the area of the 7 BP is 4.088 square units. And 14.5 plus 4.088 is 9.412 square units. That is actually the area of the green shape. Repeat again, if you found out that the area of this green shape equals to 9.412 square units in its size. We finished with the first question. The next step, I present to you the second question, and we solve the second question in two different methods. In the second question, our task is to find out the length of this line segment AP that is equal to x. We have to find out the value of x. So in the drawing, we have a semicircle, AB equals to 10. That is to say the diameter of this semicircle equals to 10, therefore the radius must be equal to 5. In addition, we know that line segment BC equals to 6 units in its length, AP equals to PC equals to x. Again, our task is to find out the length of side AP that is equal to x. We have to find out the value of x. So first of all, we define the center of this semicircle. This point is point O. Again, the diameter AB is 10. Therefore, the radius OA is 5. The radius OB is 5. We join points O and P together by straight line. OP is also the radius of this semicircle that is equal to 5. By doing this construction, we get the associated triangle AOB. AOP, right triangle AOP is an associated triangle because side AO equals to side OP equals to 5. And we have the rule that in front of equal sides in the triangle there are equal angles. So if we relate to the associated triangle AOP, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the associated triangle AOP, alpha plus alpha is 2 alpha. Therefore, this furthest angle must be equal to 180 degrees minus 2 alpha, according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. Likewise, the big triangle APC is an associated triangle because side AP equals to side PC equals to x. So in the big associated triangle APC, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. But we have only found out that the size of this angle is alpha. Therefore, the size of this angle must be also equal to alpha because they are equal to each other. So in the big associated triangle APC, alpha plus alpha is 2 alpha. And therefore, this third missing angle must be equal to 180 degrees minus 2 alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 180 degrees minus 2 alpha. So in the next step, I copied the big associated triangle APC and the small associated triangle AOP in a new page, and we put that those two associated triangles are similar to each other according to angle similarity rule. So those are the two associated triangles. This is the big associated triangle APC. This is the small associated triangle APO that are copied from the original drawing. So what those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles they are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, and therefore they are also equal to each other. So I can prove that all the angles of the big associated triangle APC are correspondingly equal to all the angles of this small associated triangle APO. Therefore, those two associated triangles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, we realize that the following relationship exists between their sides. We will divide the side AC of the big associated triangle APC over side AEP of the small associated triangle APO is equal to side PC of the big associated triangle APO over side PO of the small associated triangle APO. Okay, AC is 16, AP is X, PC is also X, and PO is 5. So in total, we have found out that 16 over X equals to X over 5. Here we first multiply this equation, and finally found out that X times X is X squared equals to 16 times 5. Here we took a root out of this equation and finally found out that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only be 5. So in total, we found out that the left of this line segment AP this is equals to X, it is equals to either 4 times square root of 5 units in itself, in terms of numbers. The length of line segment AP this is equals to X, it is equal to 8.94 units in itself. So we finish with the first method. In the next step, I presented to you how to find out the length of line segment AP this is equals to X according to the second method. In the second method, we use the rule that we already used in the first question. The rule says that the perpendicular to the base of an associated triangle bisects the base. Again, the perpendicular to the base of an associated triangle bisects the base. Triangle APC is an associated triangle because AP equals to PC equals to X. So from the vectors P, we draw perpendicular on the base AC. AC in total equals to 10 plus 6, that is 16. Again, from the vertex P, we draw perpendicular on the base AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AC, the base AC, this point is point M. According to the rule that I mentioned, the perpendicular PM bisects the base AC. AC is 16, therefore each half must be equal to 8. The first half MA is 8, and the second half MC is also 8. PO, so we define the center of this semicircle, this point O. The diameter AB is 10, therefore the radius is 5. So OB is 5, OA is 5, OB is 5. We join points O and P together by straight line. OP is also the radius of the semicircle, that is 5. So what is the length of this small line segment OM? OM equals to AM minus AO. Again, OM equals to AM minus AO. So OM equals to AM, that is 8, minus AO, that is 5. So in total, OM equals to 8 minus 5, that is 3. The length of this short line segment OM is equal to 3 units. In the next step, I copy the right triangle OPM in a new page and implemented on it the Pythagoras theorem. Okay, this is the right triangle OPM that are coming from the original domain. The hypotenuse PO equals to 5, OM equals to 3, PM is the missing side. So according to the Pythagoras theorem, in this right triangle OPM, PO squared, that is the square of the hypotenuse, equals to PM squared plus MO squared. PO is 5, therefore PO squared is 5 squared, that is 25, and it is equals to PM squared. PM is the missing side, so we leave it as it is, plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total, if we found out that 25 equals to PM squared plus 9, here we subtracted 9 from this equation, and finally found out that PM squared equals to 25 minus 9 is 16. So PM squared equals to 16. Here we took a root out of this equation, and finally found out that PM equals to the square root of 16, that is 4. The missing side PM equals to 4 units in itself. This is the missing side PM, that is equals to 4 units. In the next step, I copied the right big triangle APM in an equation, we implemented on it the Pythagoras theorem. This is the right big triangle APM that are coming from the original domain. According to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to PM squared plus MA squared. AP is x, therefore AP squared is x squared, and it is equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16. Plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 64. So in total, x squared equals to 16 plus 64. 16 plus 64 is 80. So x squared equals to 80. Here we substitute 80. We substitute 80 by 16 times 5. So x squared equals to 16 times 5. So here we took a root out of this equation and found out that x equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total, in both methods, we found out that the left of line segment AP is equals to x. It is equals to either 4 times square root of 5 units in itself, or in terms of numbers, the left of line segment AP is equals to x. It is equal to x is equal to 8.94 units. Okay, thank you very much.